Afternoon, everybody. I think we'll get started. So this is going to be the second of three talks that are focusing on the National Research Platform, NRP. And we have Mohammad Sada joining us again to lead us through this one. The previous talk is already posted, both the YouTube video as well as the slides in the shared folder. So if people need to go back and reference that, it's certainly available. But this talk is going to be focusing a little bit on a use case, the ESnet SENSE and layer 2 quality of service path orchestration piece. So I will hand it over to Mohammed.
Right. Hello, everyone. For those of you who are attending this one without watching or attending the first one, welcome. For those of you who saw the first one, welcome back. Uh, I will give a brief recap. So whoever is on the call who hasn't seen the first one, you can follow along just fine. Uh, as Jason mentioned, this is part two of a three-part series. The first one was an introduction to the National Research Platform, as it was on the 27th of June. After the Friday after that, of course, with the 4th of July. So our second part, which is now, is on July 11th, and the next one is going to be on the 18th. So the first one was a general introduction about all the resources and hardware and software environments that the NRP provides. And for this one, we're going to be focusing on how to conduct network experiments and construct construct network testbed experiments on NRP using L2 paths that are orchestrated with quality of service using ESnet SENSE, which we're going to be talking about a little bit. And for next Friday, we're going to dive deeper with a more developed use case of using ESnet Sense services to conduct an inter-testbed networking experiment. So an experiment that goes beyond the scope of the of NRP and its Kubernetes cluster called Nautilus to involve other environments. And the demo we're going to show is the Fabric testbed. And it's going to involve provisioning SmartNICs and potentially FPGAs and how to conduct those experiments since both NRP and Fabric have FPGAs that can act as P4 programmable SmartNICs. And I'm just going to go ahead and get started just to give you a brief overview and recap. So the National Research Platform is, simply put, it's a partnership of more than 70 academic institutes. And it is the evolution of what was initially the Pacific Research Platform project. And it came to address the rising demand for cyber infrastructure and address the disparities and differences in accessibility and gaining access to these cyber infrastructure resources, especially with that, since the end of Moore's law is a reality now. And of course, with the rise of artificial intelligence, machine learning, uh, all domain sciences are heading towards not only heavy GPU involvement, but also looking towards novel architectures, different hardware types that are in many ways heterogeneous, that the domain scientist might face difficulty in knowing how to set up and dedicate tremendous resources towards setting up these hardware architectures, whether it's through time or cost or so on. And that's what one of the main things that the National Research Platform comes to address in providing all hardware and software environments and resources in a way that we can call generally available, where scientists from any domain can reserve the hardware, reserve the software, provision both, be able to use both with reproducible examples, trying as best as we can to eliminate the barrier of entry, both in gaining access to hardware resources that researchers might not have access to, and by setting up the environments that reduce friction as much as possible. And of course, these efforts are led by researchers at the San Diego Supercomputer at UC San Diego and the University of Nebraska at Lincoln and the Massachusetts Green High Performance Computing Center, MGHPCC. And of course, it includes contributions by NSF, DOE, DOD, and a massive community of many research universities and R&E institutes and organizations both in the United States and in multiple international locations outside of the United States, constructing what we have today, which is the Nautilus cluster. So everything in the National Research Platform operates under one Kubernetes cluster that we call Nautilus that has hardware now spanning across three continents and continuously expanding. The Nautilus cluster has been in continuous operation through PRP to NRP for more than 6 years now, and it provides many services, many file systems, for example, like the SUF file system, the CERN VM file system, S3 storage, we have a very high focus on measuring and monitoring with providing tools like Perfsonar, Traceroute. We export every single metric that we can to Prometheus and visualize it with Grafana. And we have Thanos for S3 compacted Prometheus data for 5 years of storage. And we provide easy points of access as well for users who are not very familiar with Kubernetes or not very comfortable in writing YAML, understanding all the systems. We have GUI points of access like public Jupyter Hub instances, as well as providing users with how to set up instances of Jupyter Hub, as well as many other software tools that are there to provide the research community with something to the research and education communities with something to advance their work. So we host our own instance of GitLab with CI/CD, so users can build their Docker images, for example, in containers inside the cluster. Nextcloud for file storage and sharing, Overleaf for LaTeX, and so on, and many other services. And the cluster today is more than 430 nodes. I believe the current number is 440 nodes as of now, with more than 1,500 GPUs, more than 50 FPGAs of different kinds, uh, Bluefield 2 SmartNICs and DPUs, smart SSDs, and programmable Tofino switches, and many other hardware architectures, hardware resources. And some of the network hardware resources that we have is 32 P4 programmable Xilinx Alveo U55C FPGAs. And that's going to be a main discussion point on our next talk next week when we show you how to provision these FPGAs as SmartNICs and how to connect them to topologies and conduct network experiments with them. Of course, they're very capable with the features like DPDK and various command line tools that are available in the ESnet SmartNIC tool stack, which is designed around the Alveo cards to provide them with not only SmartNIC functionality, but you can sort of consider it a switch on that is sitting on the edge to provide programmable networking. We also have 16 bitware 520N MX Stratix FPGAs. Those are, of course, those bitware FPGAs are Intel Stratix 10 FPGAs, and but on paper they are also SmartNIC capable. We're in the process of discovering more about that and developing the pipeline so users can provision them as SmartNICs in an easy way. We have two Agilex 7M FPGAs also on paper by Altera. They're P4 programmable. And we have three Xilinx Alveo SN1000 or SN1022. So both names are the same FPGA. The model number is actually SN1022, and it's the same card as the U45N for those of you who are familiar with it. The U45N is simply a rebrand of the same FPGA. And we have many secondary NIC interfaces. What I mean by secondary NIC interfaces is that the cluster itself is uh, 440 host servers. Uh, Traditionally, each server has a network interface card or more, and the network interface card has one port that is used for deployment, for connecting to the cluster, to the networks, and so on. But the secondary port, that is what can be provisioned for network experiments, and that is what can be plumbed through to inside the pods and used for network experiments, and that's what we're gonna do today. And we have other resources as mentioned, like the NVIDIA Bluefield 2 DPUs and smart SSDs. Of course, what smart SSDs are in this instance are FPGA powered SSDs, so smart computational storage that is sitting on the edge with programmability, and P4 programmable Tofino switches that are also developing pipelines into how we can provide them to the research community to provision these resources. And just this is a brief map of how the cluster looks like today. We showed the same map a week ago, and just in a week, you can see that the numbers have went up, and that is just to show that the cluster is ever expanding. Of course, so let me just go back. If you want to look at this dashboard, this is a live dashboard. It's hosted on dash.nrp-nautilus.io. And like I said, we have 440 nodes currently connected to the cluster. You can see here, just a brief mention, we have various kinds of GPUs. You can see here between creating the slide and presenting it, the numbers for GPUs have went up. And uh, just to show the variety and heterogeneity in the kinds of GPUs that are on the cluster, as well as novel architectures like the Qualcomm Cloud AI 100 Ultra cards. Those are inference optimized cards that are that with a very easy to use work pipeline and loading LLMs, for example, and other generative AI models. Uh, in a modular fashion, since each card is four systems on a chip. And of course, these are available to the research community, and we provide documentation along with documentation on how to use all of our services for whoever is interested in provisioning these cards with the rising demand for inference for scientific domain research. And that was a recap on the National Research Platform in the Nautilus cluster. Now I'm going to talk about the ESnet Sense in general. After that, I'm going to go deep into how ESnet Sense can be used on NRP. So, in general, so Sense is short for Software-Defined Network for End-to-End Network Science at Exascale. What that means is that it's a network management system. And with the orchestrator being let me call it the centerpiece, of it to provide tailored network services. So what that means in tangible terms is that it allows users to orchestrate L2 and L3 paths with various other configurations so they can be provided with end-to-end services for their network workloads. And uh, just sharing a few slides courtesy of the ESnet Sense team and Eustace Balkis from ESnet. And this is what the ESnet Sense architecture looks like. You can see it's API driven. So the orchestrator itself can be talked to through an API, and each site, so each host switch or server has a service called Site RM, which is short for Resource Manager. And of course, it's an intent-based API that shows a lot of metrics and a lot of details that are very beneficial in orchestrating these resources with features like discovery before establishing a path and setting up negotiation for quality of service. You can set up quality of service in various ways where it can be guaranteed quality of service or best effort to provide more flexibility. And of course, looking at the life cycle of the established paths. And of course, the BSNet Sense folks have provided a tutorial. I'm gonna pause here a little bit for whoever wants to grab the QR code. This is a brief tutorial on how to use the orchestrator uh, for establishing L2 and L3 paths, also courtesy of Eustace Balkas. All right, if anybody wants to catch and didn't get a chance, just please feel free at any point, whenever you wanna have a question, just feel free to unmute and ask right away. And also, just one use case of YesNet Sense is using it with Rushio. And Rushio, the easiest way to explain it in very simple terms, is a data management solution or service that allows the users to share. It's for data movement, basically. So Rushio is used in conjunction with ESnet Sense for data movement at CERN and various LHC locations where users can hook up or connect the Sense orchestrator to Rushio to find and establish the best paths that the data can move across. And this is what the current Rushio testbed looks like in conjunction with Sense. All the paths here are 400 gigs, 400 gigabit per second. Path to UNL is 200 gigabit per second. You can see here various sites like national labs like Fermilab and you have UCSD, CERN, Caltech, and Amherst, and so on. Of course, the orchestrator also provides various features that we're not gonna have enough time to go into today with the NRP, but it provides L2 and L3. For our demonstration, we're just gonna focus on L2, and you can start multipath orchestrations, and you can also, it has various features like hop by hop monitoring and BGP, which are very high in demand and have various benefits. And just to talk a little bit more about how ESnet Sense plays into Nautilus and how it can act as a very beneficial tool that allows us to conduct network experiments on the National Research Platform. So Sense comes in as the first step. So let's say I'm conducting experiments on two remotely distant nodes. So I want to conduct any experiments, any research that involves any plumbing of L2 paths between two pods, so two containers essentially. They're running on two different two geographically different nodes, so two distant servers, sorry. And that's one use case where I might want to use Sense, and that's how it plumbs the path. So by using the orchestrator, it establishes the path over a tagged VLAN. So I can set a VLAN tag and it'll start the path over that VLAN. It'll show me on the orchestrator how it goes through topology. And it will start the VLAN interface as a MAC VLAN interface on the actual host, so on the node. So whoever has bare metal access to the node can see, for example, we show an example here. So node-2-7 is an actual node. It's an actual server at the San Diego Supercomputer Center, part of Nautilus. You can see when I start a path, let's say I set up the VLAN for 3112, you can see that it sets up the interface, which is what makes it much easier for me because at that point I have the interface on bare metal. As a user, I just have to provision it to be sort of plumbed through from the node to the pod. And that's where Multus comes in. So Multus is a container network interface plugin. It allows us to provision these interfaces from the from the host node onto pods and also VMs if you're using KubeVirt VMs. And it does so through what is called a network attachment definition, which is defined by a simple YAML that allows me to set what the host interface is with many other parameters as well, and I can just let the interface show up on my pod and start an experiment, which is something we're gonna get to do hands-on today. But before we get to, I mentioned that it starts the paths through a topology, and just want to make sure I'm conveying what topology that is. And what I mean is here in this context is the article sense topology. And the article sense topology connects various sites that involve a lot of ESnet sites. So you can see here the map on the top left, you can see ESnet sites. And on the top right, you can see Internet 2 sites. And it connects many of both. And it also connects to AL2S endpoints from Internet 2 backbone. And also, you can see on the bottom side, on the bottom right, it's a picture of the same dashboard that I showed earlier that shows the various national research platform sites. Of course, all of these maps are cropped just purely into the United States just to fit in one slide. But you can see that there are international locations, and that has very interesting use cases. And on the bottom left side, you can see the Fabric testbed. So for those of you who don't know what the Fabric testbed is, it's a federated testbed for conducting network experiments, and it provisions a lot of network resources between switches, smart NICs, traditional NICs, and shared interfaces, and so on. That allows users to have a sort of sandbox, safe environment where they can do their network experiments, break stuff, and basically work on their research. And that's what we're trying to provide in conjunction with on the National Research Platform by using ESnet Sense for our use cases. And we do that through our in-house built operator. So the operator allows us to use the orchestrator as NRP users without having to necessarily ask for access to the direct orchestrator through ESnet. We can go through NRP to ESnet and provision it just like how we provision all resources on Kubernetes with a simple YAML. So what we did here is we defined a custom resource definition for a sense path. And in our sense path, we're trying to make it as simple as possible. So I just have to set its name and namespace, where it's running and what it's going to be called. And we only need four pieces of information to start a simple L2 path, and with the fourth being optional. So we need a bandwidth, and that is the quality of service bandwidth. Here, 1,000 is 1 gigabit per second, and we need the two endpoints. So to be able to start a path between two endpoints, I need to know the URIs for the endpoints. Of course, we're in the since our operator, it's a project that is still in development. It's early access. We've provided a form for whoever wants to access it, but it's in continuous development. It's in continuous adding of features where we're trying to implement a feature where users don't need to know the entire URI, they can just pass the node name. So in our case, that would be node-2-8.sdsc.optcomputer.net. That is an actual Nautilus node. That's the name of a server, and node-2-9 is another one. And just by providing the two endpoints and bandwidth, you have your path. The fourth parameter that you can pass, and the fourth value is VLAN. So when you pass it, you can set the specific VLAN tag that you want to use for your path. But it is an optional path because there is a value any that you can pass to the orchestrator. At that point, it automatically sets a VLAN tag that is available. So in our case, applying this YAML leads to this sense path, which you can see it goes through our operator. The status, it's fetched back from the operator. You can see this is an example of a failed one, and you can see that it has a return codes for failed paths, so you can match that to know why it failed and create it at timestamp and the VLAN that got returned from the orchestrator. So this is in cases where you don't set a VLAN, you can see it in status, so you can know how to uh, provision the interfaces. So that's method one of provisioning using the operator, which is simple YAML. After that, in Kubernetes, you can see your own sense path and you can see its status and how you connect it to a pod. That's where Multus comes in, like we mentioned, through a network attachment definition. But we also have another handy feature where you can just annotate your pod with a sense path and use the name that you define for the sense path. And by you doing so, you patch your pod where we using the operator create the network attachment definition for you and add its definition to the add its annotation to the pod so it automatically uses it. And of course, there's another method of provisioning where you don't necessarily set the sense path explicitly. You just annotate the pod that you're starting on a specific node that you wanted to target another node at a specific bandwidth with VLAN, like we mentioned, being optional. What that does is that it starts the path, creates the sense path object, and updates its path from updates its status from the orchestrator, creates the network attachment definition. Like we mentioned, patch this pod so it has the network attachment definition and the interface show up inside the pod, inside its shell. And the main thing here is that before all of that, the first step is that let's say I have two pods doing so. So node-2-7 and node-2-6 going to each other. Before it creates the sense path, it looks to see if the specified VLAN I specified is something that already has a path. So this way I can define two pods. So one that is going to 2-6, that's two node-2-6, one node-2-7. Then the operator will understand that those two pods are meant to be plumbed together. So takes that into consideration as a factor. Of course, all paths after that are cleaned up, so they're not left lingering. So everything is ephemeral, and right now it's the way we're setting it up is 7 days of a path, unless requested extension. In the future, as a future feature that we're developing is auto extending based on use. So if it's in continuous use, it's always there, and that's how it gets processed. But like I mentioned, the Sense operator is a project that is in ongoing development, and of course, we have provided a QR code for early access if you want to check it out. This is a Google form. The code name for the project that acts as sort of a wrapper for the operator is called the Seam project, and if you're interested in using the operator and exploring it, we very highly welcome that. We very highly appreciate that, and we always value feedback. This is the QR code here, and the tiny URL leads to the same form. And I'm just gonna pause here for whoever is catching it. And since I paused, if anybody has any question up to this point, please feel free to just unmute and ask. All right. And now we're just gonna go to a hands-on demo part where you can follow along. To follow this tutorial, you don't need to be an active NRP user. We added a service account that is ephemeral. It expires in a few hours, but it's just there so whoever's on the call can follow this tutorial very easily without having to be an active NRP user and have all the necessary permissions for the levels of access for network experiments that I'm going to explain in a little bit. But also feel free to catch the QR code and the URL before I gonna pause the presentation here and go onto my browser and follow the same link. All right. So I hope you can still see my screen. So this is where the link takes me, and you can see here we have two notebooks. So we have one notebook called single node Multus, the other is called two node Sense. And of course, so this is my notebook. This is going to show me a simple experiment that I'm going to go over very briefly that starts a network experiment using Multus. This one is before using Sense. So for the sake of simplicity, I'm going to assume I don't need any paths plumbed. I'm starting an experiment on the same actual physical host, on the same server. And then I don't need a plumbed path. I'm just using bridge interfaces using Multus. And the goal here is to show you an example of using Multus. And of course, we're talking to Kubernetes through Python, so we're installing through pip. And traditionally, the main way of access through kubectl and the CLI tools. But this is just for the sake of demonstration and having one notebook that is using a Python kernel for the sake of simplicity. Like we said, we're using a service account token here. It's provided in the notebook. This is ephemeral. This expires within a few hours. So whoever wants access, feel free to reach out to us. Provided the links for how to reach out to us. You have the contact link where we have our various ways of reaching us through email, through our matrix chat, where all the community lives, and you can talk to other members of the community and request technical support and user support. Like I said, we're using this service account token, and the API servers, of course, our Kubernetes server, controller IP address, and the namespace we're going to be running the experiments in. For the sake of demonstration, we're using a namespace called Seam, which is the code name for the project. And this cell right here is just to verify access with the API. Then we're going to create the network attachment definitions. And let me switch to my terminal here. So this is what you're seeing here in my terminal. This is a command line tool called K9s or K9s, and it's just a simple way of showing and interacting with Kubernetes that is much easier and more intuitive than using kubectl natively. And you can see here, so network attachment definition is a resource, and you can see here we have plenty of network attachment definitions that we're using. So if I click Y, it shows you the YAML. You can see here it's what it looks like. So the type of the network attachment definition and the subnet uses and provisions, the range start and end for IP addresses, and gateway IP, and so on. So in this example, here we're passing our network attachment definition, or NAD. Uh, we're using the range between 100 and 200. You can see here we're trying to apply this range and created a network attachment definition. You can see here NAD name. We're calling it bridge network, HRTLT. 0. You can see here that it created it. If I sort them by age, it's right here. So I can verify that it's up in Kubernetes. And uh, if I run back, I have my network attachment definition. I can create the pod, and we're generating a random name. So whoever is running the pod is using the same random suffix that we generated for the network attachment definition. So there's no conflict for whoever is following this live. And this is where we're naming our pods. So we're using the same suffix and we apply it. You can see here, actually, let me show it here. It's easier to see. Oh, so this is the manifest. I haven't applied it yet. Here we go. So you can ignore the warnings because they're about HTTP and HTTPS. You can see it created my pods. Let me click on Y to show you the YAML. And of course, so this is what Multus added, but this is what we defined in our YAML. So we used in K8s v1 CNI cncf.io/networks, which is how we basically annotate to use Multus. We just use the NAD name. So we go back here. This is what we named it. And we're just using the NAD name. You can see it here. That's all we need to add to our pod. But our pod is using a node selector to land on node-2-6. It's starting a container that has a busybox image that sleeps for an hour. And it's privileged. And that's one thing I want to lead to is that if you want to be able to use network functionalities and network attachment definitions effectively for network experiments, you need to run privileged pods, which is something that is not allowed by default on the National Research Platform. And that is one thing where you're going to need the sort of special access and running those experiments on the National Research Platform, which you can coordinate with us as admins to get access to. But for following this notebook, since we're using the service account, you can reproduce this experiment and run in the same namespace. Of course, you can see we created the pods carefully, successfully. Sorry, and this cell is just to wait until they're running before running the other commands. Uh, this cell is just grabbing the IP addresses. Of course, we can see here, so pod 1, you can see here, pod IP, you can get the IP here and IP here. And it's a simple task. We're just pinging from one pod to the other. Since we're using BusyBox, we don't need to install anything. It comes with ping, simple ping test of 10 packets. And test connectivity is just a function that pings from a pod, provided an IP. So ping pod B from pod A and ping pod, sorry, wrong comments, from pod B. And as you can see here, this is us starting a very simple network experiment. And of course, you can add many network interfaces, not just the one Multus interface, to do more elaborate testing. But this is just to serve as a simple Multus experiment on the same node, so the same host server. Now to use Sense, I'm just going to show you a more elaborate experiment that uses two nodes. So those are actual two physical servers in SDSC, node-2-6 and node-2-7. And of course, both of these nodes are on the Sense AutoGL Sense topology. And very similar to how I did my first experiment, install Kubernetes, connect to the namespace, to the Kubernetes API through Python. And now step 4, here the extra step here is that I need to have a sense path through the orchestrator. So like I said, if you want to get early access to the sense operator, please feel free and we highly encourage it if you want to test it out to fill out this form. If you click on it, so this is the Google form and you get to test it. Right now it's still in development, so it's not ready for public release because things might break as it is in development. But this gets you access to the Sense operator, which is a specific use case for NRP users to start endpoints. And here, one thing to mention is that the endpoints don't necessarily need to be two NRP nodes because as we mentioned, there's different endpoints in the topology. So this is how you get access to do NRP and fabric experiments, for example, because the endpoints could also be fabric sites. And of course, you can also see if you can get the Sense orchestrator access directly from ESnet, and if potentially if you're also interested, if you're watching this video or attending this talk, and you're interested in adding sites to the Audible Sense topology, you can also contact the ESnet Sense team. The website for ESnet Sense is very straightforward. It's just sense.es.net. So sense.es.net. And here you find all the information you need and how to contact the Sense team. And of course, to show you the brief overview of the orchestrator, you can see here. So this is the official ESnet Sense orchestrator's interface and how it looks like. You can see here. Let me show you one. For example, for our demo, let me show you one instance that we started. If you look at its intent, you can see here how it's starting. This is our URI here set using Node-2-7. And this is the name of the interface on Node-2-7, which is the secondary interface, like we mentioned, that we're using, as the first interface is dedicated for deployment to connect the node to the cluster. Similarly, we're doing the exact same thing on Node-2-6, and we have our VLAN tag as any, which means assign what is available. We have our quality of service class set as guaranteed capped, which means it is guaranteed quality of service. I'm always going to be getting 1 gigabit per second, and I'm not going to go over that. And of course, this is how you can provision with the orchestrator. The orchestrator itself has a Python client for whoever is interested in checking that too. It's called sense-o-py-client. And you can connect to it through requests over the network. You can also connect to it through Python, and there's command line tools as well to connect to the orchestrator. And what we're trying to provide here is another added layer for NRP users through our operator. And this is a brief instance to show you an example of what it looks like. And here I'm just showing the instances that I started with the operator. So you can see here, this is a list of all of my instances. I started all of these using the orchestrator directly, but for the sake of demonstration, over the I started a path over the operator using this instance. And you can see here, I can create another instance. Let me call it my dash path dash two. And of course, each user gets a dedicated list of the namespaces they're in that they're allowed to run Sense in. For me, I set these to be seen, for example, in the Sense operator, which this runs in. And endpoints, this instance shows four examples. Of course, for users, it's going to be populated with all the available endpoints in an easy to read fashion. But let me say I'm starting a path between node-2-8 and node-2-9. Oh, sorry. Let me start it. And I'm not setting the VLAN, so I'm asking for it to be randomly assigned. And I'm using 1000 megabits per second. And of course, I'm running it in Seam. And it's pending. And now just to show you what that looks like in Kubernetes, if I use, so I'm in the Seam namespace. I can look at sense paths. And you can see here that it is, if I click on YAML, it shows that it is ready. Okay, since path marked as successful in demo mode and state is ready, and you can see here, this is the other namespace because it shows another one in the other namespace called my path. And you can see here, also successful. Of course, they show up here. Of course, the operator is quick to mark as ready as soon as it sees a sign of success. So create committed means it is under creation. See, the service has been successfully established by the resource managers. If it fails for some reason down the road, it does propagate that it failed. But as long as you're seeing ready, it means that things are going well. Then the feature here to implement is that to show that it is actually between pending and ready. But once that starts, you can go ahead and use it. And that's what we're going to focus on here. So step four is having the sense path in one of the ways that we mentioned. Step five is to creating the Multus network attachment definitions. And here we're going to be creating two simultaneously since we're using two nodes. And these are the paths that I went ahead and started over the orchestrator, and these are for the sake of demonstration. So they're set up for whoever is following along, they can use any of these VLANs. As long as no one else is using it, it should be available. If it fails, that means you can use another VLAN and so on. And you can see here, I'm creating my network attachment definition very close to how I did it in the first demonstration through Multus, except that I'm setting the type as VLAN, a Mac VLAN, which is this is the master interface on the node. So the physical nodes, the orchestrator starts the actual interface on the node, the VLAN interface, and I can just use that as the master and set the type as Mac VLAN and add my subnet, my gateway in a coherent way so there's no collisions and there's so pods can route to each other. And I can go ahead and create it. And you can see here, if I look at my network attachment definitions, I'm looking in the wrong namespace. We're using scene. So network attachment definitions, you can see 16 seconds ago, I started this NAD. Of course, to reduce collision, the NADs can be used by one pod at a time. So it's the NAD itself doesn't specify a node. So if you have nodes with the same interfaces, you can use the NAD across nodes, but not across pods. And we're created. Sorry, this message here is actually earnest. It's a -2. That's what we called our interface, our NAD, sorry. We're using the same interface on the host because on both nodes it's called VLAN.4013. You can see I have two NADs now. So I'm going to use node-2-6 for one and node-2-7 for one. And you can see here because our ranges differ a little bit. So, and that is for IP address assignment. So I'm having a range of one because I want my IP address to be 10.251.87.161 on this and .162 on this. And I just go ahead and create my pods. The only thing special needed for my pods is just using the networks annotation, like we mentioned, with the name of the NAD that we're using and that connects it. So you can see this is our pod on node-2-6 is using this one. Node-2-7 is using this one. Of course, the NADs are similar in nature. The thing that differs is the IP address range. So we can switch and it would still work correctly. And that's the only thing we need to add for Multus to attach the interface to the node. But to be able to ping from the pod, which isn't a capability that's provided by default, I need to add extra capabilities to my pod through security contexts and capabilities. And of course, just like running privileged pods, this is not something that is allowed by default. This is on a case by case per namespace exception for namespaces that are running network experiments. And I'm requesting the relatively modest resources because I'm just gonna ping. And if I apply my pods, you can see pod dash node dash 2-6 created and -7 created. And you can see here, you can see 9 seconds ago they were created. And I can just use the same one to make sure, same code block from before to make sure they're running. And just install ping, because just to show you a brief example, because we're using Ubuntu, for example, for these pods. And since this is communicating through the API, this might take a little bit, a few minutes, and then I'm pinging each node from the other. So each pod, sorry, from the other. So test connectivity, same function as earlier. You provided a pod name and an IP address, and all it does is ping 4 packets from the pod to that IP address. So for pod on node-2-6, I provided it the IP address that is allowed on the range for node-2-7. So this address here, I got it from my network attachment definition for node-2-7. And this right here, same thing, but for node-2-6, just to have them ping each other. I'm just gonna wait on this for a little bit just to make sure it's running successfully. And uh, all right, here we go. And just to briefly go over the operator while this finishes, uh, the operator, the goal here is to have it also implement the functionality where it automatically creates the network attachment definitions. So users can, one click of a button, we're trying to create everything with a GUI, so it reduces the friction. It can reproduce the recipes of success that we have in adding click of a button, fill out a few fields, select with pickers, and have your path ready with the network attachment definitions and the way to provision it with Multus through one line instead of manually doing the same process we're doing where we're defining the NADs, checking on the path, and doing all of those things. Of course, with the next feature to be implemented is that let's say I pick an endpoint here and an endpoint here. The next feature to be implemented is to show me the range of VLANs that I can provision to be within the VLAN range of overlap between the two endpoints. And of course, add a negotiation process, which is these are all orchestrator features. We just want to implement them on the operator and to add a negotiation for bandwidth and uh, different ways of requesting quality of service. So best effort or guaranteed capped or so on. And you can see here it installed ping on both pods and it pinged from both pods. And to briefly show you what's going on the pods. So this is my pod on node-2-6. And you can see here, so let me just very quickly just installing the tools to show you ifconfig. And I'm going to do the same thing here. All right. All right. So this is my interface. And this is one of the neat things about using Sense is that I don't need to worry about VLANs and I don't need to worry about what's going on under the hood. I see my interface on the pod as a native interface with the IP address, and I can just ping from IP address to IP address. So you can see here, this is node-2-6, it has 161. This is node-2-7. Of course, not the node itself, but the pod on the node as 162. And I can ping one from the other. And that's exactly what we did in the script. I'm just showing it to you from the pod's shell. And all right, here we go. So it would be one to ping the other one. And of course, with ifconfig, you can notice the packet numbers went up with pinging. And this is one brief example. Pinging is a very simple example where it can be done. Of course, it's just to demonstrate connectivity. But of course, this is just the stepping stone because this is to establish connectivity. Once you have the connectivity, there's various interesting use cases that you can use this with, especially when there's a heavy amounts of data with data movement, and especially when with use cases that involve smart NICs and smart components to networks and programmable networks. and use cases with the GPUs and AI workloads as well, where you can have explicit control over the paths taken and how the data is traversed. And like I mentioned, next week it's going to be a demonstration more advanced that involves the SmartNICs and involves an experiment similar to how we had the what I just showed you, the second notebook, but it'll go over the Fabric testbed and the National Research Platform. Sorry, let me start from current slide. And of course, some of the things we're going to cover is provisioning FPGAs and SmartNICs on NRP. Of course, we do that over graphical user interface web service called Coder that allows us to provision those FPGAs in very easy, reduced friction way, smooth way, and provisioning network interfaces on NRP with Multus, just like how we did, and provisioning SmartNICs on Fabric, which is very similar to how we provision FPGAs on NRP, since it's relying on the similar FPGA models with the Fabric testbed having U280 FPGAs, Xilinx U280, Alveo U280. And we're also going to be using Fabric facility ports, which essentially means connection points that we can specify a VLAN on. And those facility ports are on the Sense topology. So once we have our node, our Fabric facility port, whatever VM or in Fabric terminology node, which means a VM, is connected to that facility port can gain connectivity into NRP. And then we're going to use the sensor orchestrator and operator to establish L2 paths in a simple experiment that goes through UCSD's one of UCSD's NRP nodes to the UCSD Fabric side. Of course, time permitted, we can also show different sites, so it's geographically distant, and a brief connectivity test and brief experiment, hopefully something more interesting than pinging, between a Kubernetes pod and a VM that is running on Fabric. And the easy way to be able to follow along, and we're going to make it as reproducible and as easy to follow along as possible over the Zoom call within the lunch break. Uh, is to both have NRP credentials and Fabric credentials. So to get access to the Fabric testbed, you need to have a Fabric account and a Fabric project, which if you were interested in following along, please make sure you have one. For NRP, for persistent access, you need an account, but similar to how we provided a service account token, we're going to also provide a new one next week on July 18th with our next talk. And this concludes our talk. Thank you all very much for attending this talk. This is the QR code for the National Research Platforms website, which is nrp.ai. And it has all the information you need on how to get access, how to produce the exact same experiments we had, how to use other cluster services, and how to reach out to us as operators and admins. And thank you all for your time. Just gonna end it here. And whoever has a question, please feel free to unmute and ask right away.
All right, thank you, Mohammed, for going through all of that. Very comprehensive. So everybody has the ability to just unmute. If you do have a question and you want to do that, please do, or you can use the chat room, or you can raise your hand and we'll acknowledge you. There's also a couple of ESnet folks that are responsible for Sense on, so if anybody else wants to chime in or add in anything about Sense, certainly do as well.
If there's no questions, Mohammed, why don't you show iPerf running between those two pods, showing the QoS.
All right, let me.
I love a challenge.
All right, let me check if it. Okay. That's that's expected. All right, here we go. All right. All right, feel free to correct me if I'm wrong. Was iPerf-S? Or, let me check actually.
Yeah, that's it.
All right, just double checking. And Let me grab the IP address. All right. Oh, so it's my bad. All right, it's just IP, iperf-s and then ping from the other one, right?
No, iperf minus C in the IP address of the other one.
Here we go.
You have to have a dash S on one host and a dash C on the other. Are you going to the right IP?
Uh, yep.
Oh, there it goes.
Okay, let me try it again.
Close to 1 gig.
Yep. I mean, that's pretty impressive. Let me try, see, 989, 981.
Yeah, there you go. Cool.
All right, and well,
iperf 3 might be more verbose.
Yeah, there's a litany of options to make it more verbose.
Right.
Well, proof that it works. So thank you both again for going through that. And Mohammed, if you want to send me the slides again, I'll make sure that those get posted along with the video. And as Mohammed said, next week will be the last talk in this series. So hope everybody has a good weekend, and we'll talk to everybody next week.
all right, thank you.
Thanks all.